In question D1, they want us to find the x value where the function here, y equals f of x, has a local maximum, local or relative maximum. So you can kind of see here that this is a maximum point, but also over here, this is a maximum point. And actually right here, this is a relative or local maximum point. And then we're going to use slope to justify that. So here I'm going to say f has a local max at both x equals 4 and x equals, we said that was x equals 10. I know I'm ignoring the endpoint for a moment here. And the reasoning. Because at these x values, f is continuous. I want to just throw that in there. F is continuous. And here's the slope justification, and the slope, notice what happens to the slope. The slope went from positive slope to negative slope, and that occurs all the times where we have a maximum. With exception of the endpoint, we can use slope to justify a maximum. The slope goes from positive to negative. F is continuous, and the slope goes from, I want to say the slope of f, goes from positive to negative, local max. Know the concept well and then worry about the wording. The concept's what you have to understand. I'll also throw in here now then that f has a local endpoint max at x equals -3. But it's the interior ones that I am most concerned with. Then a similar analysis is going to hold here for local mins. If I just come over, let me find a color, yellow maybe? Okay, here, local min, see it? Local vertex min. Not here, no, because it's getting smaller, the function, and the function continues to get smaller, so that's not local min. So at this yellow, there's a local min. At this yellow, there's a local min. And then again, at the end point, we have a local min. And then the wording is going to be similar, except that the slope goes from negative and then changes to positive. Okay, so I'll just read this off now then. F has a local min at x equals 0 and x equals 6.5. Because of these x values, f is continuous, and the slope of f goes from negative to positive. And then I put the little bullet at the end. F has a local endpoint min at x equals 17. In question E, we're going to be talking about a concept of concavity. So if here's a function, y equals f of x, this thing is what we call concave upward. See how the cave is facing upward, and then concave downward is like this. The cave is facing downward. Now sometimes the function does like this, and you can see that it's concave up for part of it, and then it changes. That's called a point of inflection, but then it changes concavity like that. It doesn't have to be as obvious. If I have like a bell curve here, here's the point of inflection. So this is concave down in the middle, but at some point then it goes concave up. Even though this approaches some asymptote, it is concave up. And then we're going to use slope to justify that. So I'm going to give you just a quick analysis of this. So this is concave up, and we want to decide what's happening to the slope. Here you can see at this point the slope is negative. Let's just say it's -10, the slope. And then here it's also a negative slope, but it's a little less steep, so maybe it's -5. And then here -1, and then here horizontal tangent, slope is 0. And then it increases. Let's say the slope is 2, and then the slope is 15, and then the slope is 29. Do you see what's happening here? These slope values are getting bigger. So the function is not increasing, but the slope is increasing. So concave up is associated with increasing slope. The same holds for concave down. So the slope here, positive 20, slope here, positive 5, slope here, 0. Do you see how the slope values are getting negative? Or, sorry, are getting smaller, negative 17. So concave down is associated with decreasing slope. Let's first do our visual. Concave up. So see how we have this concave up portion, still concave up, still concave up, still concave up. Now linear segments do not have concavity, so it's not concave up nor concave down. So then it's concave up. Do you see somewhere in here it changes concavity to concave down? So on these two parts of the function, f is concave up. So we're going to say f is concave up on, now we always use parentheses for this, -3 to 2 in union with 5, 2, and then there's some estimation somewhere in this ballpark, so we're just going to say 8. The reasoning is because the slope of f is increasing on this interval. Nice. E2 wants to know concave down, so we'll get a visual of that. I'll take a dark blue. Linear segments do not have concavities, no, so let's see, concave down, good, and then concave down again. Excellent. F is concave down on the x interval of, we said that was 8 to 14 in union with 14 to 17. And that's because the slope of f is decreasing. Not the function's not decreasing, but the slope is decreasing on this interval.